Okay, folks, I'm going to attempt to create a pencast using a new piece of equipment, which is a 22-inch high-definition Wacom tablet that we're going to have in the recording studio, and it's available for all BME undergraduates to use. So I'm going to use it to talk about how to solve problem SMS 3.3, which we solved together in the problem-solving studio, and at least some of you were able to finish it, and it was on homework. So on the homework, so everyone will have done it by the time you listen to this, but I think it is still useful to have me demonstrate how I'm expecting to go about solving these kinds of problems. So first, of course, you read and understand. The problem says that corn steep liquor contains 2.5 weight % dextrose and 50 weight % water. The rest of the liquor stream is solids. Beet molasses contains 50 weight % sucrose, 1 weight % dextrose, and 18 weight % water. Now, I'm not actually going to read this whole thing, but what I like to do when I'm solving a problem like that is as I'm reading it, I'll go ahead and start drawing the diagram. So we have coming in to this device, which basically it appears to be a mixer, so we may want to identify it as such. I think I'm going to go to a thinner stroke pen. So I'm going to call the corn steep liquor, I'm going to call that stream C, and as we're reading the problem, we can begin to annotate the diagram. So we have dextrose, and I think it's worthwhile to write it out once, but we can put like an abbreviation for it, and we're going to put the weight %. And really what I like to do is work with weight fractions just to be consistent. We have water, which I'm going to simplify as W. And we want to put the right number of significant figures there as well. And then we have solids, which is the rest. And we can calculate that later. We also have beet molasses coming in. So I'm going to call this stream B, beet molasses. And that stream contains sucrose, which I'm going to call SUC, and it contains 50% by weight sucrose, and then we have dextrose, 1%, and water, 18%, and the rest of it is solids. So we can figure out how much that is later as well. And then it talks about an exit stream, which I'm going to call P for product, and that contains 2% dextrose, 12.6% sucrose, and then we have water and solids, so we don't really know how much we have of those. And we're missing the fact that we're adding water to the stream. So we want to add that stream, but here I'm going to call that W. Notice that there are no masses identified, so we're going to have to establish a basis in order to solve this problem. So I'm going to call the mass of C. I'm going to solve this problem for 100 grams of C, corn steep liquor coming into the system. And if you look at what they're looking for, so that's the basis actually, so this is actually part A of the problem. We got that done already. But what they want to know is the mass fraction of water in the product stream and of solids in the product stream. And they want to know the ratio of the mass flow rate of the water stream to the corn steep liquor. So this is a good diagram. We know we have a basis established and we know what we're looking for. So we're ready to get started on the rest of the problem. Okay, so now the next thing we want to do, we want to write our mass balance equations. Because, as I've mentioned many times, that is the truth, basically. We know mass is conserved, and it's a great way to reduce the degree of freedom. It's information that we can use to help solve the problem. So you can write one for total mass entering, the total mass in each stream entering and exiting the system. So actually, before we do this, we have to I don't know why I can't erase that. There we go. Before we do that, we want to say accumulation equals in minus out plus generation minus consumption. So this is the general mass balance equation. But in this case, these are zero because there's no reactions. And it's a steady state system. So there's no accumulation. So in is equal to out is our simplified mass balance equation for this problem. So you can write this. You can write equations, whoops. So you can write equations of this form for each species in the system. And for total mass. So it's very good practice to do that and to go ahead and identify each one of these equations. So we can write the total mass balance equation. That's going to be all the streams coming in. So we said that we had 100 grams coming in stream C. We have the mass that's in stream W. We don't know what that is yet. And the mass in stream B. Those are all the input streams to this mixer. And all those, only one output stream of the mixer. So they're got the total mass, all of those combined will equal the total mass flowing on stream P. Okay, we can write a balance equation for dextrose. It's 2.5% of stream C. It's 1% of stream B. And it's 2% of stream P. So dextrose is only coming in two streams and exiting in stream P. So we took care of that. We can now write a mass balance equation for water. It's 5% stream C. There's a water stream that's 100% water. And then there's stream B, which is 18% water. And that's going to equal to the mass of water in stream P. We can write one for solids. So I figured out that there must be 47.5% in stream C, because the other, if you look at the other mass fractions, they were 0.5 and 0.025, and they have to add up to 1. So the mass fraction of solids in stream C has to be 0.475. So that's where that comes from. And then we're going to have 31% of the mass of B has to be solids. Again, if you add up 0.5 to 0.01, that's 0.51, plus 0.18 is 0.69, so that means there has to be, these have to add up to 1, so the mass fraction of solids in stream B is 0.31. So that's where the 0.31 came from. And that's going to equal to the mass of solids in stream P. And then finally we can write one for sucrose, half the mass of stream B is sucrose, and it only comes out in one stream. It enters in one stream B and exits in one stream. It's 12.6% of stream P. So this is the way that we can write these are 5 mass balance equations that we can write. Note that only 4 are independent, because if you add the mass balance of each species, D, W, S, and SU, they're going to sum up to the total. You'll end up with the equation that's for the total mass balance. So there's 5 different equations you can write, but only 4 of them are independent. So now I think what you want to do is, before you start jumping into the problem, you want to make a plan. In other words, you can actually say, in step 1, if you look at the equations, and I didn't actually number them, I should have, we could say that this is equation 1. Actually, let me do that in a different color. Okay, so we labeled the equations 1 through 5 in Roman numerals. So now if we can refer to that in our plan. For example, the first step is you could solve equation 5 and 2 for, at the same time. You can, by solving them simultaneously, you can find the mass of stream B and the mass of stream P. So that would be a good place to start. And then after that, you'd have enough information to solve equation 1 for the mass of stream W. And you would then have enough information to solve equation 3 for the mass fraction of water in stream P. Because remember, the mass fraction, this term right here, which I'm about to circle, we could write that as equal to mass fraction of P, mass fraction of water in P times the total mass of stream P. So if we would replace that into the equation after we've done steps 1 and 2, we would have enough information to solve for the mass fraction of water in stream P. And then step 4, we would now be able to solve equation 4 for the mass fraction of solids in stream P using the same logic that I used for step 3. And there's one more thing you want to do. You want to check the answer that you come up with. One way of doing that is to make sure that the mass fractions of all the species in stream P add up to 1. So that's one thing that we can do. Okay, so now let's go ahead and execute our plan. Whoops. Okay, so you want to execute the plan. So step 1, we have this equation. The mass flow rate of B is equal to 0.252 times the mass flow rate of P. And so if you plug that in, so we're solving equations 5 and 2 at the same time. I'm going to plug that into the other equation. Okay, and then we can just do a little bit of algebra. And then from this, we can find that the mass of P is equal to 143 grams. And the mass of B, so we're going to solve this equation now, is equal to 36.0 grams. So I probably didn't explain this very well, but this is basically equation 5 multiplied by 2. Okay, so we took equation 5, and then we plugged that into equation 2, because equation 2 had a term right here. In equation 2, this was equal to 0.01 times the mass of B, which, as you can see from here, is equal to 0.00252 times the mass of P. So that's where we got that equation from. And then we just went ahead and solved for the total mass flow of streams P and B. Okay, so now we're going to go to step 2. Okay, so step 2, we were going to solve equation 1 for the total mass of stream W. So substitute for what we just learned. Equation 1 is 100 plus the mass of stream W plus the mass of stream B, which we just figured out was 36 grams. And that is equal to 0.02 times the mass of P, which we just figured out is 143 grams. And if you solve this equation, you'll find that the mass of stream W is 7 grams. Okay, so then we're going to do step 3. And step 3 is to solve equation 3 for the mass fraction of water in stream P. So equation 3 is 0.05 times 100, so that's 5, plus the mass of stream W, which is 7, plus 18% times the mass of B, which we said we figured out was 36 earlier, And that is going to equal to the mass of water in stream P, which we could write as the mass fraction of water in stream P times the mass of P, but we already know that is 143 grams. So we can solve for the mass fraction of water in stream P from these equations, and that's going to equal to 0.129. Next we want to go ahead and do step 4, which is solving the mass balance, the fourth mass balance equation, the mass fraction of solids in P. Okay, so if you look at equation 4, it's 0.475 times 100, so that's 47.5, plus 31% times the mass flow rate of B, which we said is 36. And that's going to equal to the mass fraction of solids in stream P times the total mass flow rate of stream P, which, as we said before, is 143 grams. And so we can solve for the mass fraction of solids in P, and it's going to equal to 0.410. Okay, and then we got the last step is to check our answers. So let's go to a new page. And we want to check our answer. And I think one way of doing that, we said before, is to see if the sum of the mass fractions that we calculated for stream P is equal to 1. It definitely should, so let's find out. So the sum of the mass fractions of the components of stream P is, okay, it's going to be 0.02. We knew that from before, that 2% was dextrose. We knew that 12.6% was sugar, and then we just calculated that 41% of it is going to be solids, and 12.9% is going to be water. And so the question is, does all of this equal to 1? And the answer is, it adds up to 0.685. Oops. What went wrong? Okay, so this is why we always want to check our answer. Something did not work out. Let's see if we can figure it out. Okay, well, I went back and inspected my diagram and the problem statement, looking for mistakes that I made, and it turns out that the mass fraction of water coming in stream C is 0.5, but in my mass balance equation for water, I actually put 0.05, so that's a mistake, and we have to fix it. So the mistake I made was that I wrote the mass fraction for water in stream C as 0.05. But it should be, and I had it right in the diagram, but I didn't get it right in the equation. Should be 0.5. Okay, so let's repeat. I'm going to repeat our calculations, starting at step 3. Okay, so repeating step 3. Now we wanted to solve equation 3, and that's the one that I messed up. for the mass fraction of water in P. So now, when we rewrite that, it's 0.5 times 100, not 0.05. So we're going to have 50 plus 7 plus 18% of 36 is equal to the mass fraction of water in stream P times 143 grams. So now when we solve it, we find out that the mass fraction of water in stream P is actually 0.444. Okay, but everything else should be correct. So my mistake only messed up that one answer. So now we can go ahead and go to step 5 and check that the sum of the mass fractions in stream P is equal to 1. So let's go ahead and do that again. So 0.02. Okay, so that's the dextrose. We have 0.126. That's the sucrose. And then we just calculated that the water is 0.444. And previously we figured out that 41% of this was the solids. And the question is that equal to 1? And the answer is yes, 1 is equal to 1 when you add that all up. So the answer is correct. So now, finally, we can go ahead and report our final answers. Okay, so we already said that A, the question was, what is the basis? And our basis is that the mass flow rate of stream C is 100 grams. Question B wanted to know a bunch of mass fractions. So the mass fraction of dextrose in stream P is 0.02, and of sucrose in stream P is equal to 0.126, and of water in stream P is 0.444, and the final species in stream P is a mass fraction of 0.410. And then finally the last question was, what is the ratio of the mass flow rate of stream W, the water, to the corn steep liquor? And we've already solved for both of those, so we know what the answer is. 7 grams to 100 grams, to the ratio of the mass flow is 0.07. And basically we just box our final answer and we're done. So hopefully this will help clarify exactly the process by which you can solve mass balance equations. Start out with a diagram. Be very careful that it correctly reflects what the written statement says, and then you can use that diagram to formulate your mass balance equations and use those to solve the problem. But always check your answer, because it's easy to make a mistake, and by checking the answer you're more likely to find that mistake, and then you go back and fix it, get the right answer in the end. That's it for now. I hope this helps. Take care.